infinite sequences. I'm going to begin with an example. An infinite sequence is basically an endless list of numbers with a certain pattern in them. The easiest infinite sequence that I can think of is the sequence of natural numbers. 1, 2, 3, 4, 5, forever. So that would be an infinite sequence. Another example of an infinite sequence is, let's say, the list of all the odd numbers. So 1, 3, 5, 7. That's an infinite sequence. You can think of all the multiples of 2. All the multiples of 2 are going to be 2, 4, 6, 8. That's also all the even numbers. And you can see that there is a pattern here, and that pattern could be captured in a single expression, an. So we can say this goes on, and then at some point you have the general term of the sequence. In this case, it would be 2n, and then go on, goes on forever. So if n is 1, you get 2. If n is 2, you get 2 times 2, 4. When n is 3, you get 6. When n is 4, you get 8. So this is called the general term of the sequence. Each one of these numbers is called a term for the sequence. So here you have an example of a sequence. The first term is A1. The second term is A2. The third term is A3. And then you have the general term AN. And it goes on forever. So when I look at this, I can see that the first one is 1, then you have 2 over 3, then you have 4 over 9, then you have 8 over 27. I realize that there is a pattern here. So for example, this is 2 over 3 to the power of 2, because 2 to the power of 2 is 4, 3 to the power of 2 is 9. And this would be the same number, 2 over 3 to the power of 3, because 2 to the power of 3 is 8, and 3 to the power of 3 is 9. So if I want to write this sequence and include that general term, it would be 1, 2 over 3, 4 over 9, 8 over 27, and then it seems that it's 2 over 3 to the power of n, and it goes on forever. And you can see in this case, in order for it to work, I need to begin with n equals 0. Because if n is 0, I get this to the power of 0, 1. I get the first term. Then when n is 1, I get the second term. When n is 2, I get the third term. So I can also express that like this. I can say this is 2 over 3 to the power of n, where n starts at 0. So this is also another notation for expressing the same infinite sequence, which is definitely more compact and precise. And what does it tell us? It tells us n begins at 0. If I plug in 0 into this, I get 2 over 3 to the power of 0. I get the first term. Then n is 1. I plug in 1, 2 over 3 to the power of 1. I get the second term. Then 2 over 3 to the power of 2, then to the power of 3, and this is also the general term. So here, let's take a look at the definition of the infinite sequence. An infinite sequence, an in curly brackets, is a function whose domain is the set of positive integers. So what you plug in for n could be, they could be integers. So 0, also we can also plug in 0 like the example I showed you, 1, 2, 3, 4. And what comes out of this function are the terms of the sequence. The function values x, a1, a2, a3 all the way, these are called the terms of the sequence. And the term an, or the nth term, that is called the general term of the sequence. So here you have a couple of notes. It says the sequence an is called is also denoted by this. So I can just say, use curly braces, put the general term inside, and then I can indicate where does n begin. N could begin at 0, n could begin at 1, and then it goes on forever to infinity. So that's why it's called an infinite sequence, because it's a list that never ends. Sometimes it is convenient to begin the sequence with AK. In this case, the sequence can be denoted like this. So sometimes n does not begin at 1. So I already give you an example where n begins at 0. You may have a situation where n begins at 3. So for example, if I have something like this, let's say 2n plus 1, where n begins at 3 goes to infinity, I just know that the first term is going to be when I plug in 3 into this. I get 2 times 3, 6, plus 1, 7. Then I plug in 4, I get 9. Then 5, I get 11. Then 13, and so on. Okay. Any questions so far? Example 1, it says list the terms of the sequence. So here we have some sequences, n over n plus 1. And if nothing is mentioned about where the index starts, we're just assuming that it starts at 1, because that's the convention. So since there is nothing here, I just assume that n begins at 1. And if I want to create the sequence, I plug in 1 into this, I get 1 over 2 for the first term. Then I plug in 2, I get 2 over 3. Then I plug in 3, I get 3 over 4, and the pattern continues. So those are the first 3 terms of sequence in part A. Then we have part B, root n over 2 to the power of n minus 1. And again, since there is no beginning given, I just assume that n begins at 1 and continues to infinity. So if I plug in 1 here, I'm going to get root 1 over 2 to the power of 0. 2 to the power of 0 is 1. So I just get 1. Then I plug in 2, I get root 2 over 2. Then I plug in 3, I get root 3 over 2 to the power of, if I plug in 3, root to the power of 3, that's 4. Then I get 4, root 4 over 2 to the power of 3, that's 8. And the pattern continues like this. So that was part B. Part C, the general term is -1 to the power of n, root n minus 2, and here it is indicated that n begins at 2. So the first number that I plug in into this is going to be 2, and also I noticed that here, since I have -1 to the power of n, this is going to be an alternating series, that is an alternating sequence, that is the terms are going to be positive, negative, because -1, when you raise it to the power of an even number, it's going to be positive. So -1 to the power of 2 or 4 or 6 or 8, that's going to be 1. But -1 to the power of an odd number, like -1 to the power of 1 or 3 or 5 or 7, this is going to be -1. So the terms are going to alternate between plus and minus. So if I plug in 2, the first term is going to be -1 to the power of 2, which is 1 times root 2 minus 2. That's going to be 0. That's the first term. Then I plug in 3. When I plug in 3, I have -1 to the power of 3. That's negative. So I get negative root 1, which is just -1. Then I plug in 3. No, I already plugged in 3. I plug in 4. it's going to be positive. I get positive root 2, then negative root 3, then positive root 4, and so on. So it's going to alternate between negative and positive, and then just increases under the root sign. Yeah, so here you have the answers in the book. Any questions about example 1? Example 2 is asking us to find the general term or the nth term of the sequence. So we have to look at this pattern that we see here and guess what the general term should be. So let's see. When you look at the numerator of this, you can see that it's just increasing. It begins at 2, then 3, 4, 5. It keeps increasing like that. And when you look at the denominator, it also, I can write it as 2 over root 1. Then the second one going to be 3 over root 2. Then 4 over root 3. Yes, and it keeps on going like this. So I can say that the general term is n plus 1 over root n, and n begins at 1, goes to infinity. Now, if I plug in 1, I get 2, then 3, then 4, then 5. If I plug in 1 into this, I get root 1, then root 2, then root 3, so it works. Make sense?
Could we have done something else?
What do you mean?
Because I said that it would be n over square root of
Yeah,
n.
very good. You can also do that. No problem. You can write it as n over square root of n minus 1. Is that what you mean? And
Yes.
then begin n at 2.
Exactly.
It's exact same sequence. So there's no unique answer to this. But the thing is, if you expand this out, beginning at 1, you get these sequence of numbers. If you do the same thing with this one, as it indicates, plug in 2 first, then 3, then 4, you're going to get exact same sequence. So this is good. This is also good. Okay, next example. So here I can see these are powers of, this is 2 to the power of 3, this is 3 to the power of 3, this is 4 to the power of 3. So I will have some n to the power of 3 at the bottom. And on top, it's just 1, it doesn't change. So n to the power of 3, on top I have 1, and n begins at 1, goes to infinity. So first I have 1 to the power of 1 over 1 to the power of 3, that's just 1. Then I have 1 over 2 to the power of 3, that's 1 over 8. Then I have 1 over 3 to the power of 3, that's 1 over 27. Then I have 1 over 4 to the power of 3, 1 over 64, and so on. Okay, and when I look at this one, part C, I can see this is an alternating sequence. That is going from positive to negative, back to positive, back to negative. So for this one, there is definitely a negative 1 to the power of n involved, because that negative 1 to the power of n will have the alternating effect. And it begins, and if I begin at, for example, 0, the first term is going to be positive. So I can say it's negative 1 to the power of n. And then for the rest of it, I just have a 1 on top, and I have a the denominator is just increasing from 1 to 2, then to 3, and so on. So I'm just gonna put that over n. But there is a problem here, and that is the first term is going to be negative like this if I want to begin at 1. So I can solve that problem by just putting a plus 1 here, and that will solve the problem. Because now the first term is going to be negative 1 to the power of 2, which makes it positive, over 1. So 1 over 1, 1. And then the second term is when n is 2. And now I have negative 1 to the power of 3, That's going to be negative. And that's what I want. Over 2. So this works. I could write it like this. Negative 1 to the power of n minus 1 over n. N begins at 1. That also works. I could write it like this. Negative 1 to the power of n over n plus 1, and then start it at 0. That would also work, because first it's going to be positive, negative 1 to the power of 0, then negative, then positive, then negative. That's what I want. And at the bottom, if n begins at 0, I will have a 1, then a 2, then a 3. So any of these 3 could be the answer for part C. Any questions? So you can see in the book, you have the second answer I provided here, negative 1 to the power of n minus 1 over n, where n begins at 1. Okay, so you can also graph these sequences, just like you graph a function. You can graph these sequences. And the way you graph it is that you graph n versus an. So you have a sequence like this, a1, a2, a3, a4, all the way. And the graph could be something like this. You have 1, 2, 3, 4. What happens if I plug in 1? I get a number. What happens if I plug in 2? I get another number. What happens if I plug in 3? I get another number. So you can just graph n versus an, and you will have the graph of a sequence. And here you have some examples. If you graph n plus 1, so n plus 1, if you plug in 1, you get 2. So it passes through the point 1, 2. Plug in 2, you get 3, passes through the point 2, 3, then 3, 4, then the point 4, 5, then the point 5, 6. Here's another example, n plus 1 over n. If you plug in 1, you get 2. If you plug in 2, you get 3 over 2. If you plug in 3, you get 4 over 3, and so on. And here you have the values, 1, 2, 2 and 3 over 2, 3 and 4 over 3, and so on. And here you have an example of an alternating series, very simple one. The values of this one is going to be alternating between negative 1 and 1. So first it's negative 1, then 1, then negative 1, then 1. So if you graph it, it's going to be like this. 1 and negative 1, 2 and 1, 3 and negative 1, 4 and 1, 5 and negative 1, this point here. So they just behave like functions, except for they are discontinuous and they have only values defined at integers. Any questions? Okay, then. So just like functions, they can also have limits. So we're going to study the limit of these sequences as n approaches infinity. So we want to know what's going to happen to the sequence as n gets bigger and bigger. So if you look at this graph, for example, you can see if I think of n increasing forever, what's going to happen to an? These points, they just form a line. Yes, these are points that are on the line x plus 1, because this is the sequence n plus 1. These are points on the line x plus 1. And what happens as n approaches infinity, an would also approach infinity. So the limit does not exist here. And if the limit of the sequence does not exist, you would say that the sequence diverges. Or if you look at this one here, what happens as n approaches infinity? The values of the sequence, they just alternate between negative 1 and 1. That means they will never approach a certain number. So in this case also, the limit of the sequence does not exist, and you can say that the sequence diverges. However, if you look at this one, and if you take the limit of n plus 1 over n as n approaches infinity, you can see what's happening here. This can be done by the dominant term technique. This is the same as the limit of the dominant term on top is n. That's the term with the highest power. The dominant term at the bottom is n. So it's going to be 1. So the values of this sequence are going to approach 1, as you can see here. It's like having a horizontal asymptote here. So the first is 2, then you have, when you plug in 2, you get 3 over 2, then you get 4 over 3, then you get 5 over 4, then you get 6 over 5, and this trend keeps on doing, and these values are going to get closer and closer to 1. So if as n approaches infinity, an approaches a certain number L, then we say that the limit of the sequence is that number L, and we say that the sequence converges or has the limit L. So limit of a sequence, let an be a sequence. We say that the sequence an converges or has the limit L, and we write it like this, same notation as we use for functions. If the term of the sequence an can be made as close to L as we please by taking n sufficiently large. So same definition that you had for limit when x approaches infinity. If a sequence is not convergent, then we say that the sequence is divergent, or the sequence diverges. Is that clear? So let's take a look at these examples. The first one, you have the limit of 1 over n as n approaches infinity. So the numerator is constant, the denominator is increasing. So it's going to be 1, then 1 over 2, then 1 over 3, then 1 over 4, then 1 over 5. And you can see that this, what happens here, the fraction is going to approach 0 because the numerator is a constant and the denominator is increasing. So this sequence converges to 0. But when you look at the next one, it's going to be root 1, then root 2, then root 3, then root 4. It keeps increasing. It's like the function root x that goes to infinity as x goes to infinity. Same story here. Root n will go to infinity as n goes to infinity. So this sequence here diverges. And I have already talked about this one. This is an alternating sequence. This is an alternating sequence. So let me just correct this. N approaches infinity. So the values of this sequence, they don't approach anything. They just fluctuate between -1 and 1. So what happens? You say that this does not exist. This limit does not exist. As a result, the sequence is divergent. So here you have the explanation. Thus, no matter how large n is, there are terms that are equal to -1 for the odd numbers, and there are terms that are equal to 1 for the even numbers. This implies that there cannot be a unique real number L such that an can arbitrarily be close to as n gets larger and larger. Therefore, the sequence is divergent. Are we good? Okay, so all those properties that you learned about limit, they also, limit of a function, they also apply to the limit of a sequence. So for example, we learned that if we have limit of f of x plus g of x, this is equal the limit of f of x plus the limit of g of x as x approaches, let's say, a. So the same property is also true about sequences. So limit of f of x plus g of x is equal limit of f of x plus limit of g of x. We can say the limit of a sum is equal the sum of the limits. That is also true for a difference. That's true for a product. That is also true for a quotient. And all these properties, they also hold for sequences. So imagine limit of an, limit of this sequence exists. So this sequence converges to a, and the other sequence, limit bn as n approaches infinity, this also exists. So the sequence converges to b. If that's the case, then limit of c(an) would be the same as c limit of an. In other words, this c here, which is a constant, since it does not depend on n, you can just move it out of the limit. So the answer is going to be ca. Limit of an plus bn is going to be limit of an plus limit of bn. Limit of an minus bn is going to be the limit of an minus the limit of bn. Limit of a product is going to be the product of the limit. So limit of an times bn would be limit of an times limit of bn. It's going to be a times b. And the same thing is true for a quotient. Limit of an over bn would be limit of an over limit of bn. And this would be the case as long as this limit at the bottom is not 0, because the division by 0 does not make sense. So we had the same properties for limit of functions, and now we see them again for the limit of sequences. Okay, let's take a look at example 5. Any questions about the properties? Okay. So find the limit of 1 over 2 to the power of n. So if I have limit of 1 over 2 to the power of n, I can write this as limit of 1 over 2 to the power of n. That would be the same as limit of 1 over limit of 2 to the power of n as n approaches infinity. So on top, I'm going to get just 1, because 1 is just 1. It's a constant. At the bottom, I can see that as n approaches infinity, 2 to the power of n is going to get bigger and bigger. These are powers of 2. So we have 1 over infinity, that's going to be 0. Make sense? Part B, limit of 2n squared plus 1 over 3n squared plus n plus 2. So I can break this into the limit of this term plus the limit of this term over the limit of this one plus this one plus this one. The method that we used with functions was that we would divide the numerator and the denominator by the highest power of the denominator. So I'm going to show you what I mean here. So if you divide the numerator by n squared, you're going to get 2 plus 1 over n squared. You do the same thing for the denominator. So you divide the numerator and the denominator by n squared. So this term here divided by n squared is just 3. This term here divided by n squared is 1 over n. And this term divided by n squared is just 2 over n squared. Now, it's going to be the limit of the numerator over the limit of the denominator. This term is going to go to 0. This term is going to go to 0. This one is also going to go to 0, so you get 2 over 3. But the method that I will accept if you do is something called the dominant term technique. And it works for sequences because n approaches infinity. it also works for functions when x approaches infinity. This limit is equal to the limit as n approaches infinity of, I just keep the dominant term. And the dominant term is the term with the highest power, 2n squared. At the bottom, I also keep the dominant term, that's 3nx squared, because this term here and this term here, they really don't matter as n approaches infinity. So these two terms, they determine the fate of this sequence. So it really doesn't matter the terms that are not dominant. And you can see that this is simply 2 over 3. So just give you a couple more examples with the dominant term technique, and you see what happens when the numerator has a bigger power, what happens when the denominator has a bigger power. So imagine I give you limit of, let's say, 2n squared plus 3n over, let's say, 5n to the power of 3 plus 1 as n approaches infinity. So here, the denominator has a bigger power than the numerator. So you can assume that since it has a bigger power, it's of higher degree, it's going to grow faster. And if it grows faster over time, as n increases, the denominator is going to be much bigger than the numerator. So this is going to go to 0. Now let's use the dominant term. 2n squared on top, 5n cubed at the bottom. As n approaches infinity, that's going to be limit of 2 over 5n as n approaches infinity. You can see this is 2 over infinity. That's 0. But what happens if I have a sequence with a numerator that has a higher power, like this? So just imagine in the numerator, I have 7n to the power of 3 plus 2n. At the bottom, I have, let's say, 4n plus 5. So here, the numerator has a higher power than the denominator. So you can guess that the numerator is going to grow faster than the denominator. And if it grows faster, this will go to infinity. Now, let's see what happens if I just keep the dominant terms. I get limit as n approaches infinity, 4n to the power of 3, 7n to the power of 3 over 4n. That's going to be limit of 7 over 4n squared as n approaches infinity. And it's clear that this is going to go to infinity. Yes, Salma, you have a question?
Yes, what happened to the 2n and the 5 below?
That's actually the dominant term technique. And but by that, I mean this limit is going to be the limit of this other sequence where there is no 2n and there is no 5. And the reason is that these two are not the dominant terms. They have no say when n approaches infinity.
Okay, so we only take what is in the front and we ignore the rest.
No, not what is in the front. You take the one with the highest power. Yeah?
Okay.
So I'm writing these in descending order of powers. So that's why you see the first one has the highest order. But the reason I am picking this is not that because it's in the front. I'm picking this because it has the highest power. This one has a power of 3. This one has a power of 1. So this is not dominant. This one is the dominant one. Make sense?